students, let us try our hands at a few questions in this CHEM 0901 tutorial number 2. Okay, so here's a question. It says when 2 moles of ice melts at 0 degrees Celsius and at a constant pressure of 1 atmosphere, 12.04 kilojoules of heat is absorbed by the system. The molar volume, which is the volume of 1 mole of a substance, or the volume occupied by 1 mole of a substance. Alright, so the molar volume of ice and water are 0.0196 dm cubes and 0.0180 dm cubes respectively. And now we're asked to calculate delta H and delta U, and also to comment on how the values of delta H and delta U compare. Now, the first thing you want to do, let's get ourselves a pointer here, or a marker I should say, so we can start to do some writing. Okay, so the first thing I would recommend is that you should consider the equation. Consider what is happening in terms of an equation. Okay, let's try that. Okay, so what you have is ice melting to give you water, liquid. Okay, that is what is happening. And so there is a volume change. The volume of the solid is given as 0.0196, whereas the volume of the liquid is given as 0.0180. So clearly there is a volume change. We can calculate a volume change, delta V. If there's a volume change, then it means that some sort of work would have been done on or by the system. Now, the water, which is the liquid, is the product. So to calculate delta V is product minus reactants. So it's 0.0, or you could say final volume minus the initial volume. Here 0 minus 0.0196. Right? And this, of course, is in dm cubes, right? Because we have to be careful not to abandon our units. Now, after doing that, let us see what this volume change is. 0.0180 minus 0.0196, and we have a value of minus 1.6 times 10 to the minus 3 dm cubes. Okay? However, we know, right? We know that delta U is equal to Q plus W, and that W is equal to minus P delta V. Okay? We know that. Now, P, the pressure given to us is in atmospheres. All right, let's move over a little bit. Work is equal to the pressure, which is 1 atmosphere, right? Here it is. 1 atmosphere is the same thing as 101.325 newtons per square meters, which is the same thing as pascals. Don't forget to put this minus sign here. You'll get in trouble for that. Times the change in volume. However, the change in volume must be in meters cubed. Now, we know that it takes 1,000, right? 1,000 dm cubes, right, to give us 1 meters cubed. So, clearly then, the change in volume would be equal to minus 1.6 times 10 to the minus 6 meters cubed. Okay? Now we have a good volume. However, there's something else that you must remember. Look at this. It says when 2 moles of ice melts. Now these volumes are molar volumes. These are volumes for the melting of 1 mole, right? Melting of 1 mole. This is the volume occupied by 1 mole. Okay, but we are not dealing with 1 mole. We are not dealing with a volume change due to 1 mole. We are dealing with a volume change due to 2 moles. So we'll have to multiply this number by 2. Okay, let's go over here and do that. Let's go over here and do all of that. So we are going to put delta V here. Delta V is minus 1.6 times 10 to the minus 6 meters cubed times 2, right? Because we're dealing with 2 moles. Okay? Now, let's check out our units, because if our units do not cancel, then it means that what we're doing is wrong. Okay? So, reciprocal meters squared cancel. It will cancel away 2 of the meters out of the meters cubed. So this will cancel here. So you end up with only meter. So at the end of the day, your answer will have units of Newton meter. Newton meter is the same thing as joules. Now let's work out the number. Let's calculate this number. Okay. The first thing I do is to multiply the minus 1.6 by 2 before I forget. So I multiply that by 2. Okay. Then multiply what I get, or the result, by minus 101,325. All right. And this is what I have. Okay, this is what I have, 101,325. Let us be sure. Let me just check this number again. It looks a little weird. And remember, you should always check the numbers that I give you. Always check these numbers. Okay, or at least follow, so that you can see if we, if we are getting into any trouble. Times 2. Okay, times 101,325. Okay, that's a better number. Okay. Alright, so let me just put my number in here. This is the number I got. Minus, actually, it cannot be minus, it has to be plus. Alright, it has to be plus 0.324. Alright, and you understand why it has to be plus. I mean, if it's a plus, you don't really have to put the plus sign, because we know if we don't see a sign, it's positive. Okay, but you can understand why it's positive, because if you think about it, you are multiplying two negative numbers. All right, so getting a positive is what is expected. So here we have it. We have calculated the work. All right, but nobody asked us about the work now. Remember that they asked us about delta U and delta H. But like we said up here, here it is. All right, we can calculate delta U from that. So delta U is now equal to, we have the heat at constant pressure. The heat at constant pressure is this number here. Okay, so it's 12.04, and it's in kilojoules, so I'll put it in joules. All right, just so all the values being used are at the same magnitude, or should I say they are of the same magnitude, plus the work, which is 0.324 joules. All right, delta U is equal to, it won't change much, as you can realize. Okay, so it's, let me just put this in my calculator. Okay, all right, so this is what I got. And remember, always plug these numbers in for yourselves, just to ensure that I am not getting into trouble. Okay, okay, so that's what I have. Of course, in joules, if you want, you could put this in kilojoules. That's not a problem. So you'll end up with, I guess, 12.040 well, kilojoules. All right, that's what we have. Now, what about delta H? Because we were also asked about delta H. Well, delta H, as we know, is equal to delta U plus P delta V, right? Okay, let's try to put some values in now. Delta H is equal to delta U. We know delta U, here it is. Here it is. So we're going to just take it and put it back here. All right, very convenient for us. Okay, I'll just put times 10 to the 3. So it's back in joules. Plus, okay, P delta V. P delta V. Okay, P delta V. Well, we know delta V and we know the pressure. The pressure is 101,325, right? Newtons per square meters. And we know delta V to be minus 1.6 times 10 to the minus 6 meters cubed. But don't forget, you need to multiply this by 2. As a matter of fact, let me get you some more space. Let me get us some more space so that we're not squashing against the margin so much and not seeing what is going on. Okay, let me just rewrite this in such a way that it is easier to see. All right, and I'm going to take all of this area. All of this area I'm going to be using, all right? Just so you can see better. Okay, I'm going to start from over here. So delta H is equal to the delta U value, which we calculated just now, 12 point, let me just write out the whole thing, seeing that I have space now, 0.32 joules plus, okay, the P, the pressure is 101,325, right? Newtons per square meters, okay? Times, okay? I'm going to put a little square bracket here, all right? Times, the volume change is minus 1.6 times 10 to the minus 6 meters cubed, right? Times 2, right? Remember the volume change was 2 times this, okay? 2 times this value, right? And this, of course, is in meters cubed, okay? Now, at the end of the day, you should get a value of, let me have a look. Let me plug these values into my calculator. Let's see, 101,325 times minus 1.6 to the minus 6, yes, times 2, yes, okay, plus, okay, and this is the value that I got, all right, and I'll even check it once more, but this is the value that I got. I got a value of, it's a comma, 0.995, and this is in joules, all right? That is the value that I got. Now, that is quite interesting. That is quite interesting because it's basically the same value, right, as the heat given off up here. This value here, it is the same value. Okay? Yes. If you think about it, if you do the rounding off and stuff, you come right back down to this value. Because if you try to put this calculated delta H in kilojoules, it comes back down to that value. And what this tells you is that delta H is actually the heat at constant pressure. All right. Here we have another interesting question. What we have here is carbon reacting with sulfur dioxide to give you carbon disulfide and carbon monoxide. What is important to note is the reaction ratio, right? As you can see, it's 5 moles of carbon that reacts with 2 moles of sulfur dioxide to give you 1 mole of carbon disulfide and 4 moles of carbon monoxide. Let's get a writing device. So the ratio, let's just put the ratio down, is 5 to 2 to 1 to 4. Now, let's read the question. It says, determine the heat absorbed during the complete reaction of 2.614 moles of carbon with sulfur dioxide to form carbon disulfide, which is a liquid, and carbon monoxide at constant pressure. Okay, all right. Now, let us go. The thing is, we don't have 5 moles of carbon. We only have, according to the question, 2.614 moles. Now, based on that, how many moles of sulfur dioxide would react? It would be 2.614 divided by 5 times 2. This would tell us the number of moles of sulfur dioxide that would react. We are just using the mole ratio to find out the number of moles of the others that are not known, because the question only told us about carbon. So that's what we're doing. 2.614 divided by 5, okay, times 2, and so it would be 1.046. In terms of carbon disulfide, it would be 0.6, well, not 0.614, excuse that, it would be 2.614 divided by 5 times 1. Okay? Alright, I'll erase those shortly. 2.614 divided by 5. And so for carbon disulfide, it would be 0.5228. For carbon monoxide, it would be, let's see, 2.614 divided by 5 times 4 would be 2.091. So for this one, it would be 2.091. Now, let's clean things up a little bit. Okay. Now, based on what we have here, all right, based on what we have here, we can calculate the amount of heat that would have been absorbed, right? Easy. If 1 mole of carbon disulfide, right, when formed, leads to the absorption of 239.9 kilojoules, right? What if only 0.5228 moles were formed? So all you have to say is if 1 mole gives 239.9 kilojoules, how much would 0.5228 give? So you'll end up with a situation where you have 0.5228, right, mole times 239.9 kilojoules, right, kilojoules, of course, being divided by 1 mole. And so the amount of heat absorbed would be 0.522 times 239.9, yes, divided by 1, and we end up with 125.22, let's say 8 kilojoules. So that is the amount of heat absorbed. Now let's say somebody asked about the internal energy change for such a reaction. The internal energy change would be delta U is equal to Anybody remember? Q plus W, right? Which can also be written as Q, which is the heat change, minus delta nRT. Remember also that delta nRT is interchangeable with minus P delta V. Okay, remember this. Work is equal to minus P delta V, which is also equal to minus delta N R T. Let me just clear things up a little bit. So we can see. Okay, here we go. Clearing things up a little bit. Okay, maybe clearing too much, but anyway. Right, so here we go then. Here we go in trying to calculate delta U. Now, delta U is equal to Q, and the Q is something like 125.2228 times 10 to the 3. A matter of fact, let's move this over a little bit so we don't run into a space problem. Let's move this over a little bit. Alright? Let's just move it over a little bit so we can work comfortably. Okay, here we go. So delta U is equal to Q, which we said is 125.228 times 10 to the 3 joules. Okay, now we need the plus minus delta nRT minus delta N. Now, delta N, we need the actual values. Now, remember what we worked out earlier. As the ratios. Well, this one was 2.614, whereas the other one, let's see, 2, we have to calculate it again because we erased it. Divided by 5 equal to that. We know that this is 0.553, yes. Let's fix these. We can see them well. Okay, all right, let's go again. 0.553. What this one now was 1 point, if you look back on what we calculated earlier, 456. All right, and this one over here was something like 2.091. All right, 2.091. Now, what do we put in the delta N? How do we calculate delta N? A matter of fact, let me just put it here. Delta N would be equal to number of moles of gaseous products, which would be 2.091 minus number of moles of gaseous reactants. On the reactant side, we have carbon, which is a solid, so we don't consider that. What we will consider is the sulfur dioxide, and we only have 1.0456. And all of this is moles. Okay, so let's just put it down here. 2.091 minus 1.0456. Okay, moles. Okay, and this minus sign is the natural minus sign which exists on the formula. Okay, times 8.314 joule per Kelvin, yes, per mole, yes, times the temperature. The temperature, if we're working with something like 25 degrees Celsius, then it's 298.15 Kelvin. All right. Kelvin here cancel with Kelvin there, mole here cancel with mole there, and you're left with joules. So let us now calculate the actual value for delta U. So 125.228 times 10 to the 3 joules plus, let me just work out that side because we like to do things in order. Okay, 2.091 minus 1.0456, okay, times 8.314 times 298.15. Okay, all right. So this is what I got for this side. Okay, that is what I got. I could also check it again just to make sure. Point 0.091 minus 1.0456, right, times 8.314 times 298.15. Got the same thing again. So seems I am on the right track. Okay, let's get the final value now. Make sure we plug everything in our calculator correctly. To the 3, yes, plus bracket minus 2591.36. All right, so this is what I have. 1, that's a comma, 4 joules. If you want to put it in kilojoules, that's no problem. All right, so that is our delta. That is our delta U. We could also calculate delta H. I know you don't see it here. See that question here in this what we have here. But you could also calculate delta H. Let's calculate delta H for the fun of it. Delta U plus P delta V, right? That's how we calculate delta H. Delta H is equal to delta U plus P delta V. All right, we know delta U already because we just calculated it. So we could just write it back down. I'll just put it in joules, okay, plus P delta V. All right, or remember that P delta V could be replaced by something else, delta nRT. All right, in this case now we don't have this minus sign on it, so it's 2591.36 joules. Okay, this is delta H. Delta H is equal. Oh, what's going on here? Ran into some trouble. All right. Okay, sorry about that. Delta H is equal to, then let's put these two values together, plus 2591.36. All right, and so we go right back to our original value of 125.228 kilojoules. Right, I just put it back in kilojoules. You could leave it in joules, it's not a problem. And this, what is interesting is that if you look at the original value that we calculated for the heat, it was this value here. And what this basically tells us is that the heat at constant pressure is the same thing as delta H. The heat at constant pressure is the same thing as delta H. That is what all of this tells us. Okay? So Just go back through these calculations again, but the fact that we come right back to this value tells us that the heat at constant pressure equals to delta H. Okay, look at this one. This one is quite interesting. This one is quite interesting. It says, find the standard enthalpy change for the reaction given below using the following data. Alright, so here we have a reaction, right, where we don't know the enthalpy change for this reaction and we are trying to figure it out. We are given these reactions, right? Here we are given some other reactions that we should use to calculate the enthalpy change for this reaction. Okay, how do you do this? Now, what you need to do is to examine the equation that you are given, which is this one, right? The one that you are being asked to find out its enthalpy change. Look at it. Look at the equations that are given, those that you have the enthalpy change values for, which are these equations up top. Identify things that are in the unknown equation, which are in these equations. What am I talking about? Okay, look at the main equation, or the unknown equation. Inside that equation, you have carbon monoxide gas. Let's look up at the top. Look at the top here to see if we have any equation or equations with carbon monoxide gas present. Well, none here, none there. What do you know? We have carbon monoxide gas here. The other question that you should ask once identifying what you're looking for is, does this equation contain the same number of moles of carbon monoxide as the unknown equation? Well, the unknown equation has 1 mole of carbon monoxide gas. And yes, this equation also has 1 mole. Good. That means you would not need to multiply this equation by any factor. Another question you need to ask yourself is the carbon monoxide on the correct side of the equation? Well, what do I mean? In the unknown equation, carbon monoxide is a reactant, right? And in the equations given to us, carbon monoxide is also a reactant. That is good because it tells you that you don't need to flip this equation. That is, you don't need to reverse it or turn it around, whichever way you want to say it. So what I could do is to go ahead and take this equation and write it down here. CO gas plus a half O2 gas reacting to give us CO2 gas. I will also write down the enthalpy value. Let me just put delta H naught up top in kilojoules per mole for everyone. So it is minus 283 .0 kilojoule. Well, it's already there, so I don't need to write it again. That's repetitive. Alright, so let's even take off this one here. Alright, good. Alright, so we have that. We're making some progress. Now let's look in the main equation again, or the unknown equation. That's what I keep calling the main equation. Well, in this, we see that we also have hydrogen gas. Look in the other equations at the top if you have hydrogen gas, right? One of them has hydrogen gas. Okay, good. Is it on the correct side? Reactant side, that is. Yes, it is. Is it present in the correct number of moles? No, it is not. This equation only has hydrogen gas. It only has 1 mole of hydrogen gas, whereas this one requires 2 moles. So this equation here will have to be multiplied by 2. Has to be multiplied, and also the delta H value will have to be multiplied by 2. Okay, and so I'm going to multiply it and write it back down here. So here I go. 2H2O gas plus okay, 2 times a half is 1, of course. and then 2H2O liquid, right? And then I have to multiply this value here by 2 as well. Let me just take my calculator. 2 times minus 286 minus 572. All right, I'll just write that back. All right, good, good. Oh, so now we only have one thing present, and this is methanol, liquid methanol. Look at it, we only have one equation left to check out. And that one equation does contain methanol in the right number of moles, but it's not on the correct side. So this equation, we'll have to flip this equation around. We'll have to flip it around. Flipping it around is the same thing as multiplying it by minus 1. Okay? Flipping it around is the same thing as multiplying by minus 1. Okay, look at what I do down here now. Okay, so here we go. Here I go. CO, gas, plus 2H2O liquid, yes, to give me methanol, CH3OOH, plus 1.5 oxygen, yes, and the value, the number we did not multiply, but now it is positive 1.5. Okay, now it is positive. Now the next thing we need to do is to cancel what can be cancelled, all that can be cancelled, and then sum what is left. Let's see what can be cancelled. And we cancel diagonally. That is, what is on the reactant side of one equation could cancel what's on the product side of another equation, and vice versa. Okay, all right, so anything? Well, we have two moles of water in this equation, right? On the reactant side, on the product side of this equation, we also have 2 moles, can cancel away like that. Okay, what do we have next? We have 1.5 moles of oxygen here. That 1.5 mole and this half mole plus this 1 mole here can cancel out the oxygens from that side. What else do we have? Do we have anything else that could cancel? Carbon dioxide can cancel with that one. I think that is it for cancellations. Now let's write down what we have. Writing down what we have left will help us to know if what we did was correct. Right? Because if after writing down what we have left, it does not look like this equation, then we did something wrong. Okay? There we go. Looking good so far. Looking good so far. Okay, looks exactly like this one. Now we need also to sum the numbers. Let's sum the numbers. Let me just get my calculator. 2 minus 283 plus minus 572 plus 715. I got minus 140. And of course, it would be kilojoules per mole as the units up top suggest. All right, that would be our answer. Let's look at another question. Let's look at another question here. Now, here we have a situation where we are given the enthalpy change of reaction for a reaction where carbon dioxide reacts with water to produce methane gas and oxygen gas. Now we're asked to calculate the bond energy, right? C double bond O, bond energy. Okay. Now we have to remember a few things in order to complete this task or to complete this question. We have to remember that all chemical reactions are both exothermic and endothermic at the same time. However, it is the extent of the two processes that determines the overall direction of energy flow. If the exothermic aspect is more significant in magnitude than the endothermic aspect, then the reaction will be endothermic or exo based on the which process is more significant. All right, here we have a question. Here we have another question where we're asked to calculate the bond energy, C double bond O bond energy, based on this equation here. Now, what we have to remember in trying to solve such a problem is that reactions, chemical reactions, are both endothermic as well as they are exothermic at the same time. However, the extent of the processes is what matters. The chemical reactions are endothermic because processes occurring on the reactant side requires energy for bond breaking, whereas processes occurring on the product side will release energy during bond formation. Now, if the amount of energy released during bond formation is greater than that absorbed during bond breaking, then the energy of the process will be negative. There'll be a net release of energy, and the reverse is also true. Now, what is clear then from all of that is that let me get a okay. Let's write something here. What is clear is the following: the exo processes plus endo processes, right, is equal to the enthalpy change of the reaction. Okay, now let's do some calculations. Let us try some calculations. Okay, one of the first things we want to do, and let me just erase this so that we can have a little bit more space here. All right, one of the first things you want to do is to be able to see the number of bonds in all of the reactants and products. For example, carbon dioxide is C double bond O, double bond O. All right, water, which we have 2 moles of, 2 hydrogen oxygen bonds. And then now for methane, we have 4 carbon hydrogen bonds. And oxygen, which we have 2 moles of that, it's 1 oxygen double bond. Now formation or the formation of bonds will cause the release of energy. Okay, now if we form 2 moles of oxygen double bonds, then it's 2 times the energy released. This is energy absorbed since it's positive, but energy released will be 2 times minus 494. All right, and this is kilojoules per mole, of course. Okay, and let us just calculate that. 2 times minus 494, we have minus 988. All right, so we have now minus 988 kilojoules per mole. Okay, now for methane, we have 4 carbon hydrogen bonds. So that is 4 times minus carbon hydrogen bonds, 410, right? 410 kilojoules, yes, per mole, which comes down to be 4 times, okay, 4 times minus 410. We get minus, this is what we have. Let's see, it's minus 16 as expected, 40 kilojoules per mole. Now the total amount of energy released total will be minus 1640 plus minus, yes, 988, all right, kilojoules per mole. Okay, all right, let's just calculate this quickly. Let's just punch these into my calculator. I have something like, this is what I got, minus, after punching in those numbers into my calculator, this is what I got, kilojoules per mole, of course. Alright, kilojoules per mole. Alright, good. That's the total amount of energy released. What about the amount of energy absorbed? Well, carbon monoxide, it has two carbon oxygen double bonds, I should say, which we don't know the value of energy required to break those. So we'll just put 2 times x. In fact, the question is for us to find the energy required to break those. Remember, we have two of them, one there, and so I put 2x plus, right? Energy required to break these oxygen hydrogen bonds. We have two of them, and we have 2 moles of oxygen, so it's 2 times 2, that's 4. 4 times oxygen hydrogen bonds, which is 464 kilojoules per mole. All right, so 2x plus 4 times 464. Yes, I got, so what I have 1856, 1856, 856 kilojoules per mole. Right, and I hope you understand why I have 4 here. Right, it's because there are 2 oxygen hydrogen bonds in a single water molecule, and then we have 2 of them, so it's 2 times 2, that is 4. Okay, all right, so now we go back to the fact that what we need is to add the endo and the exo processes, and that is equal to the enthalpy change of the reaction. Remember what we said earlier, endo plus exo is equal to enthalpy change of reaction. All right, the exo processes are over here, and the endo processes are over here. So this is exo, and these are endo. All right. Wait, I think I made a, let's just erase this a little bit so you can see. Right, we know it's endo plus exo, that is equal to the enthalpy change of reaction. Let me just write that back in a more clear fashion. So over here we say this is endo, all right, and we say the solution is endo plus exo, okay, is equal to enthalpy change of reaction. Okay, our endo process is 2x plus 1856 kilojoules per mole plus minus 2628 kilojoules per mole is equal to 890 it's 0.4. It's 0.4. We have to be careful. Let us not make such mistakes. Okay, so it's where is it? It's 0.4. Yes. Um, right. 4 kilojoules per mole. Right. Okay. So basically, what you'll find is that 2x is equal to. Let me see. 890. When we take 2628 across equal sign, it becomes positive. So it's 2000 plus 628. Yes. Minus 1856. Yes, just punching into my calculator here. Okay, so this is what we end up with. Let me show you what I got. I got 1662 kilojoules per mole. Therefore, X is equal to 1662 kilojoules per mole divided by 2, which looks to me to be equal to something like about 831.0 kilojoules per mole. Alright, for the carbon oxygen bond dissociation. Okay, another interesting question, and this question requires us to construct a Barney-Haber cycle for the formation of potassium bromide from potassium metal and bromine gas. Okay, we're supposed to label each step with the appropriate thermodynamic quantities, and in the end we are supposed to calculate the lattice energy using the data presented. We're also asked firstly though to calculate or to write rather the balanced equation for the formation of potassium bromide. Okay, here goes. Let's get ourselves a writing tool. Okay. Okay, so here we go. We can start all the way down here just so that we have enough space to do what we are doing. So what we have is a situation where potassium bromide, KBr, which is a solid, right? Which is a solid, is formed from potassium, solid, metal, yes, and bromine, Br2, gas. We have to balance by putting a half, right? Balance by putting a half, such that we only have one bromine down here. Formation is generally a negative process, and so we have this arrow pointing down. Next thing we need to do is to sublime the potassium, so it becomes gaseous potassium ions. So this is delta H SUB. Okay, we still have our bromine. Alright, gas. Okay, alright. Now we need to vaporize, well, not vaporize, but dissociate the bromine. So what we'll do is to break bromine molecule down into bromine atoms. Br, gaseous atoms, plus solid, well, gaseous potassium, I should say, sorry. Alright, so that's what we have, gaseous potassium. Okay, alright, the next thing we could do is to, and these arrows keep pointing up because all of these processes are endothermic processes. We're going to ionize potassium. Alright, so potassium ions, gaseous, plus an electron, plus bromine atom, gaseous. Let me just label these steps as was requested in the question. This one is bond dissociation. This. Okay, DISS, this. Okay, then we can do electron affinity for the bromine, so we end up with bromide, gaseous bromide, gaseous potassium ions. And then now this arrow here could be double-headed, indicating that it could go either ways. And this is normally what we call the lattice energy, represented by U, or in some books you might see delta H LAT or delta HL. Okay? But normally when you hear the word lattice energy, you hear the term lattice energy, generally means energy required to convert 1 mole of solid ionic lattice into gaseous separated ions. Okay, so that is our Barney-Haber cycle. Now, what we want to do now is to calculate the lattice energy from all of this. Now, the lattice energy, U, is equal to the delta H of formation plus delta H of sublimation plus delta H of dissociation times a half, of course, plus um, delta H ionization plus delta H affinity, AFF. I didn't even put it here. Let's put it. Delta H AFF, affinity. Okay? So let's see if we can work this value out. Let's see. So we say that U is equal to the well, we can put them in any order we like. We can put them in any order that we like. So it's 90 plus, and I'm just putting them in different orders. I'm putting the sublimation first. It doesn't matter, right? We can spin them around. It doesn't affect anything. 0.5. This is the dissociation. 193 plus 420, which is the ionization. For let me just erase this here. I'm making a mess. Let me just even erase part of this too. We don't have enough space. Maybe I write too big. Alright. Okay. Okay, let's see if we can complete the task now. Let's see if we can at least do that. Okay. Okay, so next I was going to put the ionization, and like I said, you could add the numbers up in any order. It should come back down to the same thing. All right, and next thing I'm putting is the electron affinity, and I tend to put it in brackets because of the negative sign on it. To all right. $392, and I'm telling you that you should come down to something like this: 600, 673.5 kilojoules per mole. Kilojoules per mole. That's what you should come down to. Okay? So you should work down to that one there. Okay? Right. Like I said, you can put the numbers in any order. It does not matter. But what you should know is that the lattice energy should be equal, as given here, lattice energy is equal to the sum of all those numbers. Always remember, well, in this case in particular, that the dissociation, you have to multiply that by 0.5. Okay? Don't forget that part, or else you will be in trouble. Okay? All right. Now, here's another interesting question, which asks us to construct a Barney-Haber cycle for calcium oxide. Now, let's see if we can do that. Let's see if we can do that. Well, let's start all the way down here. Give ourselves a little space. Now, calcium oxide. Okay, solid. Okay, formation. Formed from solid calcium and oxygen gas. Right, we have to take half of that. Okay, and then now we could sublime our calcium. So let's put delta H sub here. Let's put delta H formation down here. Alright, delta H sub. So we have now calcium gas. plus oxygen gas. Now, what we can do is do dissociation. Alright, dissociation for our oxygen. So we have oxygen atoms, gaseous, plus calcium gas. Okay, the next thing we could start to do now is to ionize our calcium. So delta H ionization, and we love to put first ionization, seeing that calcium is divalent. Okay, so we have calcium plus, okay, plus an electron plus oxygen atoms gaseous. Okay, now you're going to remove another electron now of calcium. Now this arrow, if you look in some textbooks, it tends to be longer than this one. Why is that? Well, because the second ionization, we expect it to be a bit more in terms of its endothermic nature. It requires more energy to pull off the second electron, because now you're not removing an electron from an atom which is uncharged, which has no charge basically. You're now removing an electron from a body which is positively charged. It is going to be more difficult. Okay, and so this arrow, we tend to draw it a little bit taller. Okay, so now we have calcium 2 plus, gaseous of course, plus 2 electrons plus oxygen gas. Okay, now we want to do electron affinity. We want to do electron affinity of oxygen. Now the first one is like this. Okay, what we have calcium 2 plus, gas of course, plus 1 electron remaining plus O minus gas. Alright, that's our O minus gas. Let's carry this minus sign a little bit closer so you don't get confused. Okay, we don't want to get confused. Okay, so first electron affinity. So this is delta H AFF1. Over here is delta H ion second. Okay, now the next electron affinity, I'm telling you, is going to be endothermic, so the arrow is pointing up. Why do you think the next electron affinity is endothermic? Well, you're going to now try to add a negative body to another negative body. That is, you're going to try to add, right? At this point, you're trying to add an electron to an anion. The anion is negative, right? That's what the name means, in fact. So you're trying to add an electron to an anion. They will repel each other. This will be very difficult. It will be energy consuming. So that's why this arrow is pointing up. Okay, so these are some key stuff that you have to pay attention to in constructing this Born-Haber cycle for the formation of lines a little bit crooked here, but you get the picture. U is E, which is the same thing as delta H LATT. Alright, so here is your Born-Haber cycle for the formation of calcium oxide. Okay.